next talk in this session, which is by Professor Shih-Chii, and she's going to talk about neuromorphic audition. And let me introduce Shih-Chii as well. So again, I think I mentioned this earlier, both Shih-Chii and Toby were part of this pioneering group at Caltech who started off this neuromorphic field. And she and Toby together direct the sensors group at Institute of Neuroinformatics at Zurich. She's currently a professor at the Faculty of Science in University of Zurich. And Shih-Chii has been very actively involved in many events in IEEE. She has been the past chair of IEEE Circuits and Systems, Sensory Systems, and Neural Systems and Applications Technical Committees. She's the current chair of the IEEE Swiss Circuits and Systems Society, and she was also the general co-chair of the 2020 version of IEEE Artificial Intelligence for Circuits and Systems Conference. Her research has received many awards. She's the recipient of the 2020 Misha Mahawald Award for Neuromorphic Engineering. She's a co-author of multiple textbooks and is also an IEEE fellow. So I think I have had the fortune of collaborating with Shih-Chii for a number of years while I was in Singapore and now while I'm in Hong Kong. So again, I would suggest to all of the people, that, especially the students attending the session, that it would be a wonderful opportunity for you to ask any detailed questions about the hardware and the algorithms that she's going to discuss, because she's one of the most hands-on scientists that I have seen. Okay, so with that, let me pass it over to Shih-Chii.
Thank you, Arindam, for such a lovely introduction. Welcome everyone to this second part of the tutorial. And so it's going to be about event-driven low compute bio-inspired processing for edge audio. Now, edge audio is sort of a hot topic, right? And it's right smack in the middle of the Internet of Things. Try to see. Oh, there we go. Okay. And so, as you know, there are billions of devices that are connected through internet or through some sort of communications network. And this number of devices is increasing tremendously. And particularly what you see is that in recent years, this market, especially for voice recognition, has increased by at least 2x. At least it's estimated to increase by 2x. And this is partially because it's much easier to interact with your devices using voice, right? It used to be like on a smartphone, you would type out stuff, but if you want to ask, for example, where the nearest restaurant is, it's much easier to just ask using your voice. And so because of that, there's a lot of interest in making audio devices or edge audio devices that have this following properties: that they're always on, that you do some sort of local processing so that you don't have to communicate through the network, that you have a real-time response, the devices are small so that you can wear them or carry them around. And because of this specifications, what that does is that it puts a constraint on the amount of power that the device can use and also the amount of memory that it can have. And so some of the tasks that are useful for audio edge devices are something like voice activity detection. So here you have a person who has, say, an Amazon Echo in front of him. And so this Echo picks up all kinds of sounds. And what you want to do is you want to detect when you hear a voice, right? Otherwise, you don't do anything. And this is called voice activity detection. And once you hear a voice, then you might be looking for a particular keyword because you don't want to process the audio all the time. And so the keyword might be hello. And so basically you look through the speech, and then if you hear hello, then you start doing something more with that speech. And the other thing that's also useful is to do speech enhancement. And what that means is that if you're in a situation where there's a bunch of people talking in the background, then what you want to do is you want to enhance the speech of that person over the background. And that's called a speech enhancement. Now, the way that this task is done is by using conventional digital feature extractors. From now on, it's called FEX. And the way that you carry out the processing is that from the microphone, you have an off-chip analog digital converter. And then on the chip itself, you have for example, a DSP block that does a fast Fourier transform, then converts it to a digital null space. Then you might do some sort of log compression, then do a discrete cosine transform on top of it to extract the features that you finally feed into some sort of network. And usually for audio edge devices, people head for binary networks because they're a lot cheaper. And what I want to suggest today is that you can also do this using neuromorphic feature extractors instead of conventional feature extractors. So remember, the output of the microphone first goes to an ADC, and then you go to an FFT plus a digital filter. And what you get is a synchronous output. And usually you have to clock the ADC at a frequency that's at Nyquist. And instead of doing this, what you could do instead is do away without the ADC and have the microphone input go straight to a set of analog bandpass filters. And then from here, generate a set of events, or you can call them spikes. And this gives you an asynchronous output, just similar in the style that you just heard about the dynamic vision sensor. Now, these blocks over here are modeled after the processing within the biological cochlea, and this is what I want to talk about more next. So the outline of the tutorial will go as follows. So I'll give a short introduction to the biological cochlea, then I'll give a survey of silicon cochlea designs and their operation. And in the second part of the tutorial, I'll talk about edge audio applications using either a silicon cochlea or a bioinspired front end. And some of the tasks that I'll touch on is localization, voice activity detection, and keyword spotting. And finally, I also want to talk about a different kind of computation. This is computation executed on demand. It's inspired by the brain. It's event-driven. And this networks process only when your inputs have changed. And this is kind of a new solution that we're suggesting for low-power hearables and IoT smart sensors. And so let me go straight to the introduction on the biological cochlea and the survey of the silicon cochlea designs and their operation. So let's look at the human ear. So the human ear is separated into three parts: the outer ear, the middle ear, and the inner ear. So the sound coming in through the to the ear goes to the auditory canal, causes the vibration of the eardrum, which then causes vibration of the bones in the middle ear. And this vibration of the bones is coupled into the cochlea, which is this organ that's shaped like a snail. And from this cochlea, you get the auditory nerve fibers that carry spikes up to the midbrain. Now, the specifications of the biological cochlea is that for human hearing, we're sensitive to frequencies from 20 hertz up to 20 kilohertz. What's really beautiful is that the biological cochlea only dissipates 14 microwatts of power. And on top of that, we're sensitive to over 100 dB of dynamic range. Now, what does this mean here? So let me show you what this means on this chart. So here, what you see here is input sound level, and also the sound level that you hear in your ear. And for 100 dB, it means that you're sensitive to sounds that go from a whisper all the way up to a jackhammer. And our ear is amazingly sensitive to this huge dynamic range. And so this is what we would like to understand is how is the cochlea conveying this information over such a huge dynamic range? And so for this, let's look at this anatomy of the cochlea. So again, here's the cochlea, which is shaped like a snail. And if you do a cross-section to the cochlea, you see that it has a particular structure where there's three fluid chambers. And so we have the scala vestibuli, scala tympani, and scala media. And in the middle of the third chamber, the scala media, you get the organ of Corti. And if you now blow it up, you'll see that the structure is very interesting. So you have a basilar membrane, and on top of the basilar membrane, you have two types of cells. These are the inner hair cells and the outer hair cells. And right above it is the tectorial membrane. And so the cells that we're interested in modeling for the silicon cochlea are these four sets: the outer hair cells, the inner hair cells, the basilar membrane, and also the afferent axons, which are also known as the auditory nerve that sends out signals up to the midbrain. And in this picture here, you see the actual electron micrograph of the stereocilia of inner hair cells and also of the outer hair cells. And interestingly, there's 3 outer hair cells for each inner hair cell. And so now let's first start with the basilar membrane. So the basilar membrane does the frequency decomposition, where if you now take the snail-like organ and you unroll it, what you see is a membrane that's very thick and narrow at the beginning, at the base, and it's very wide and thin at the apex. And so when you place something like a 6 kilohertz input into the ear, then what you see is a traveling wave that gets set up because of the coupling between the fluid and the membrane. And so you'll see that at a particular position along the membrane, you see a very large displacement, and then the energy just drops away. And what you can do now is you can present a set of frequencies, and this was done by von Bekesi back in the 60s. So present a sweep of frequencies going from, in this case, 20 hertz to 5 kilohertz, and then look at where the maximum displacement of the membrane is for the different frequencies. And so, for example, if you're sitting here at 13 millimeters from the base, then you can see that you're very sensitive for high frequencies, right? And then as you go away from the base, then you're sensitive to low frequencies. And so if you want to make an electronic model of the basilar membrane, then it looks like a set of bandpass filters, where the center frequencies varies from a very high frequency down to low frequency of about 20 hertz or so. Okay, so now let's look next at the inner hair cells which sit on top of the basilar membrane. Now the inner hair cells do some sort of rectification, so we call it a rectifier. And before I present the physiology of the inner hair cell, let's look at how it works. So now the inner hair cell has these hairs that if you now bend it in one direction, then these potassium channels will open up and the potassium ions will flow in. And then it causes a release of neurotransmitter, which then causes spikes to travel out along the auditory nerve fiber. So there were measurements already done back in the late 70s by Hertzberg and Curry, where if you look at the amount of displacement either to the right or to the left, and if you measure the response within the cell, then you can see when you displace it to the right, then the response of the cell is much higher than if you displace to the left. And so it tells you that the hair cell is acting as a halfway rectifier. And you can also present a single frequency sound to the ear and then look at the response of the inner hair cell. In this case, again, you see that you get a much higher amplitude on the positive side versus the negative side. And for 900 hertz input, again, you see a much higher frequency. And again, you can see the positive amplitude is much higher than the negative amplitude. And so it tells you that's a halfway rectifier. And lastly, we have the outer hair cells. The outer hair cells do some form of local gain control. And so this is data collected by Ruggiero and in the chinchilla. And what you see here is the gain, which is measured in millimeters per second against the sound pressure measured in Pascal. And you can see for the same sweep of frequency, depending on the loudness of the sound. So in this case, we start from 0 dB, which means it's the softer sound. Then you can see the gain is quite high compared to when you increase the loudness of the sound. And then you can see that the gain now has dropped, right? So the changing of this response curve is due to the outer hair cells, which do a gain control. So if the sound is very loud, you want to reduce your gain so that the output doesn't change as much. So again, these are from the outer hair cells. So here's a cartoon of what would happen if you now play two frequencies, a high frequency and a low frequency sound to the cochlea. And for the high frequencies, well, you can see that the base will be more sensitive to the high frequency, and then you see a set of spikes coming out along the nerve fiber. And there are about 30,000 of these nerve fibers that emerge from the ear. And for the low frequency sound, which is over here, then you can see that these nerve fibers will fire instead. And all the nerve fibers in between do not fire much. So now for the silicon cochlea designs, there have been several over the years. And usually these cochlea designs either implement the basilar membrane, which we call BM, the inner hair cell, IHC, the outer hair cell, OHC, and the auditory nerve fiber, ANF. Now, the early designs implement the basilar membrane, BM models, and usually there's three different classes of architectures. Either you get a cascaded set of bandpass filters, parallel set of bandpass filters, or you implement circuits that also model the fluid coupling that you get between the membrane and the fluid. And the later designs implement the basilar membrane, the inner hair cell, and also a model of the auditory nerve fiber. And there are also designs that implement the basilar membrane, the outer hair cell, and the auditory nerve fiber. So this is what I mean by a cascaded architecture. So here's an input coming in. It goes to a set of filters. So the output of the first filter comes the input to the second filter, and this just goes on. And also you start with the high frequencies down to low frequencies, as in the frequency response of the basilar membrane. The other architecture that's also used is what we call a parallel architecture. And so in this case, the input sound goes to a set of bandpass filters, and they have different center frequencies, going from high frequencies down to low frequencies. And this is sort of a short history of cochlear ASIC designs. And you can see the designs have already been proposed back in the late 1980s by Dick Lyon and Carver Mead. And so you get a lot of different types of designs that implement the different models of the inner hair cells, the outer hair cells. And what we have here on the top are what I call spike-based cochleas. And so these are the designs that implement a model of the auditory nerve fiber, and they produce the spikes that are transmitted using also AER, this address event representation, similar in the style of the DVS. And so the ones that I'll spend a bit more time talking about are the DAS, the dynamic audio sensor, and also the parallel DAS. And there's also been a set of designs where the auditory nerve fiber model was not implemented, but still the designs were interesting because, for example, the one by Katsiamis et al., what they did here was they tried to implement a model of the outer hair cell, the local gain control. And also recently, Zhu and Van Schaik's group have implemented the Carfax model that was proposed by Dick Lyon. So again, this is a cochlear model that also includes the gain control of the outer hair cells. And they've done this using an FPGA platform. Now with this different silicon cochlear designs over the years, so this is starting from the cascaded architecture from Dick Lyon and Carver Mead in the late 80s. And you can see there's just a variety of the number of segments that are included. So the segments are also the number of filters that you have, the dynamic range of the input, and also the Q of the filter. So this measures the sharpness of the filter. And so what these designs show is that it's just evolving all the time. The number of segments also have changed. I guess that probably depends on the chip area that you have, so, and also the size of your filter. And so, for example, the parallel filter implemented by Bowband and Corbin and Borhan is over 360 channels, which is pretty impressive. And what's important to note here is the dynamic range, because as mentioned before, the human cochlea is sensitive for 100 dB. And so you can see the cochlea that has quite a high input dynamic range is the one implemented by Rahul Sapeshka back in 2005. But it has a much lower Q than the other cochleas. So what this shows is that there's a constant trade-off between the number of segments that you want to have on your chip, the dynamic range that you would like to have with your circuits, and also the Q that you can use to control the sharpness of the filter itself. So now I'll just talk a bit more about this AER Year 2, which was the sort of the precursor to what we now call the dynamic audio sensor. And so with this cochlea, it's also the first one where we put it into a PCB, and it has all the software support similar to the DBS, and it's also binaural. And the architecture of this cochlea goes as follows. So you have the microphone coming in, goes to a preamplifier, then it goes to a cascaded set of second order section bandpass filters. And the output of each of these filters goes to a half-wave rectifier, which is the model for the inner half cell. And the output of the half-wave rectifier goes to integrate in fire neuron, also called a pulse frequency modulator. And in this case, to emulate the number of auditory nerve fibers that emerge from each channel, which could be up to 10, we had 4 integrating fire neuron models where we could adjust the threshold. And finally, we also had a resistive circuit so that we can couple the cues of the filters together. So it was a way of having some sort of fluid coupling. And so you can see the chip is over here in this package, and then a bunch of electronics that support the chip with the biases, and also taking the spikes out and sending them to a computer. And also then you have the microphones connected to the chip. And for the different blocks, so you have the second order section, which is a set of 2 amplifiers, 2 capacitors, and then a feedback amplifier connected in a positive feedback way so that you can adjust the Q of the filter. The Q deck, we won't speak much about it. If you're interested, read the paper. And then for the half-wave rectifier, it was a 5 transistor transconductance amplifier, and then a diode to output only one side of the one sign of the output, which we then could use as input to the integrated fire neuron circuits. Again, read the paper if you're interested in knowing more about the circuits. And now if we look at the desk characteristics, so here is the bandpass, the best center frequency plotted against the channel number. And for both the left and the right ear, so you can see they're quite well matched. And this is quite important because we want to use the output of this cochlea to do some interesting tasks like localization and recognition. And what you see here is the response to a chirp from 30 hertz to 30 kilohertz. So it's played over about a second. And then you can see, so this is for the left ear and the right ear. And if offsetted, the channel number here is to accommodate both ears. And what you can see here is when you play the low frequency input, then this channels fire. And then as the frequency increases, then other channels start firing. And now if you say a sentence like the fox jumped over the lazy dog, and then record the spikes from the channels, then you can see that you get a set of spikes whenever you get the word that's spoken, the fox jumped over the lazy dog. And also the spike rate that you get from the speech here is quite low. It's about 17,000 events per second. And so what we want to do now is to use the spikes to do something like the task, like localization, and also for the edge audio tags that I spoke about. So let's go first to localization. So now we have 3 types of cues that we use to localize the sound source. So the first 2 are binaural cues. And the first one is interaural time difference cues, also called ITD. And this uses, you can see a picture here. So it uses the time difference between a sound arriving to one ear versus the other ear. So if the sound is in the middle, then the time taken for the sound to arrive to both ears is the same. When it's over to one side, then it reaches the right ear faster than the left side. And if it's over on the other side, then you get the opposite. And so you can use this to tell where the sound source is in the azimuth direction. The other way of doing it is the interaural intensity difference cues. And this is usually something you can use when the sound is of higher frequencies. And finally, you can also use the monaural spectral cues due to the shape of your ear. And what we're going to use here is the interaural time difference cues. And so again, here you have a sound source where the sound arrives to the left ear sooner than to the right ear. And this can be seen in the spikes, the timing of the spikes that you get from the left versus the right ear. So the left is here in blue and the right is in orange. And if you look at the difference between the timing of the spikes that appear from the channel, so in this case, the channels are the filters with a particular center frequency, then you can see there's a particular delta T. And so what you can do is you can apply a simple algorithm, which I'm going to just show a cartoon of. So assume you have a sine wave, right? And the sine wave arriving at the left ear is the one in gray, and the one arriving to the right ear is the one in red. Now you're going to put out a spike from some phase of the cycle due to the model that we had implemented for this DES chip. And so here you have a spike on one phase, a spike on the second phase. And then for the right ear, because of mismatch, you might get 2 spikes, right, on a particular phase. And then you get a single spike on the same phase in a different cycle. What you can do now is you can look at the delta T, say between the first spike of the right ear versus the spike on the left ear. And then in this histogram that you have here, which is spaced in a way such that it encompasses between 700 microseconds to 700 microseconds, reflecting the angle that you have around the center. So you would put this, so you increase the count of this bin by 1. And then because you have a second spike, then you increase the count of the neighboring bin by 1. And for every spike that you get from the right ear, you go across to left ear and you see what the delta T is, right? So for this 2 spikes, count is 1 for the 2 bins. And now for the next spike that comes along, well, now this increases the count of this bin. And so if you keep on doing this, then what you'll see is at some point there's a peak somewhere. And this is what I'm going to show you in a demo of an actual pentil system that has both the DVS and the DAS. And what you're going to see here are spikes coming out from the DAS. Here's the ITD histogram. So it shows you a peak. And then this is the output of the DVS. Hopefully you can hear the sound too.
Here we see the spikes from the cochlea and a localization result showing the peak where the sound is located. With this, the pan-tilt unit is driven such that it orients towards movements in the visual field and towards the localized sound.
And so if I now start talking, let's see if it moves towards me, and yes, it does.
And now I will start talking, and now it moves back where I am.
All right.
Okay, so you can see the DVS is over here, and the DAS is actually off to the side, but the microphones are on the pentil system. And this was work done by Holger Finger. And you can find details of the algorithm in his paper. So the other fun bit that we've done with the DVS and the DAS is is to use the output of the sensors to train what we call a spiking deep belief network. And so this was the architecture that was around before people started using networks with rectified linear unit models. And so the idea here is that you take the output of the DBS, you show it digits, right? And then it goes through a couple of layers before you train the label layer to recognize from digits from 0 to 9. And what we did was we took the output of the DAS, the spiking cochlea, and we assigned every digit with a particular frequency, right? And so what we want to show here is if you get a visual input where it could be one of, say, 2 different digits, then you can use the audio to push the network to recognize it as one of the 2 digits. And so this is what I will show you in the demo next. Okay, so here you see an incomplete digit, which could be a 3 or it could be a 5. So ignore all these panels. All you want to see here is what the network thinks it's seeing. Okay, so in this case, it thinks it's a 3 to start off with. Okay, and what I'm going to do now is I'm going to play a particular tone to the cochlea, and the cochlea now drives the network to recognize this incomplete input as a 5. And what I can do now is to now play another tone, which is C in a second. In this case, yeah, there we go. Now it sees it as a 3. So you can flip between the 2 frequencies, and you can make it recognize. You can make the network recognize this incomplete input as a 3 or a 5. So it's a form of sensor fusion. Also, this paper by Peter O'Connor, it's also the first paper where we did the conversion, the training of the network, so we could convert a normal deep network to a spiking network. So take a look at the paper if you're interested in knowing more about these conversion methods. Okay, so next thing I'm going to talk about edge audio applications using the cochlea, and also about this event-driven computation. Okay, so when you move into edge audio applications, so similar to DBS, you have to keep the channel filter functionality simple. And the reason for that is that simpler functions in a channel lead to less output mismatch across channels. This mismatch needs to be considered because of the analog circuits in the filter. And so I'll show you now a couple of designs where we've kept to very simple functions for what we call a cochlea front end. And the next thing is to compare then the test accuracy and other performance metrics between using an asynchronous cochlea front end and a conventional front end that, for example, gives you ML filters on a different edge audio test. Now, before I go into edge audio tests, so this is a picture that's in our paper in the Signal Processing magazine. And what we do here is we look at the accuracy, the localization accuracy of either using events or spikes from the DAS, which we call event sampling, versus if you use the uniform samples from digitizing the microphone output. Okay. And what you see here is, so everything in sort of blue is from the DAS, right? And so if you have a very short time to determine where a sound source is, what this tells you, so this is over here, this tells you that the accuracy is higher using the DAS. And if you have more time, then at some point, if you use the uniform sampling method, then you can do better than the DAS. Right? So it tells you there's a trade-off, right? So if you have a short time to make a decision about where a sound source is, then you should use the DAS output. But if you have a lot more time where you can use the more conventional methods of cross correlation, then you would get a better accuracy, but you would lose in terms of the latency. And the other thing is, we also plotted the number of operations that you'll have to do to determine the sound sources, right? And so if you have something that's a small circle, that means you have few flops. So in this case, about 10 kiloflops, right? But if you look at the method that's used by the uniform sampling, then you can see that the number of flops that you have to use is much higher, right? And so if you have to do more operations, this will lead to a higher computational cost and also a power cost in your device. Okay, so now I'm going to go back to the cochlear channel implementation of the different architectures that, that we've built in the group. And so here we have the cochlear channel again with the bandpass filter, the half-wave rectifier, and then an integrating fire neuron. And the bandpass filter usually is a second-order section, again with the two amplifiers and the two capacitors, and then a feedback amplifier connected in a positive feedback way. And if you write out the transfer function and also do the measurements or the simulations of the circuit, then depending on how you tune the bias current of this amplifier versus the forward amplifiers, then you can make either a very peaky kind of filter transfer function. So this is something where the Q is high compared to something where the Q is much lower. Okay, so for the cascaded dynamic audio sensor, then usually what we do is we have a set of about 64 channels, right? And then we have channels also for the left ear and the right ear. And so that allows us to create a binaural spike output from the 64 channels for the 2 ears. But in the later cochlears, what we did was we connected them in a parallel architecture. So now the microphone input goes to 64 channels again. So we still have the bandpass filter, but now the bandpass filter is a fourth order bandpass filter. The spikes are generated not by integrating fire neurons, but rather using an asynchronous delta modulation method. But the spikes are still transmitted off using the normal AER asynchronous logic. In this case, we also have the on and off polarity spikes, which turn out to be useful when you want to do the reconstruction of the original input. Now, the on and off spikes are then transmitted off using the AER arbiter, and then you can, of course, connect now the AER output to another chip that talks AER, or also to an FPGA or to the computer. Now, the lovely thing about this chip here, which was done by Minhao Yang, is that the analog front end operates under 0.5 volts, and he could get the power consumption down to 55 microwatts for the 2 ears of 64 channels. So it was really quite a nice low power cochlear. And so the cochlear the circuits are slightly different. So in this case, instead of using the second order section where the amplifier itself is a 5 transistor transconductance amplifier, or more transistors depending on the linear range that you need from the input. In this case, he used a source follower based second order low pass filter, which came from D'Amico, presented back in 2006. And what he did was he adapted it to work for low frequencies. And so you can see it uses a differential input. Here's the positive and the negative input. Here's the two capacitors and the two currents that, depending on the ratio, sets the center frequency of the filter. Now, the question is, how would you build a bandpass filter from low-pass filter? So the circuit that was presented in this paper was a low-pass filter. But what Minhao figured out was that you could take the output of the first filter, add it to the output of the second filter, and you would get a bandpass filter. So in this case, you first compute the high-pass filter transfer function. So it's 1 minus the transfer function of the low-pass filter. And then the bandpass filter transfer function is then the low-pass filter transfer function multiplied by the high-pass filter transfer function. So when you combine this all together, what you get is a fourth-order filter, fourth-order bandpass filter, where it's a second-order low-pass filter plus a second-order bandpass filter. And so again here, this is the circuit for the second-order low-pass filter, and this is another second-order low-pass filter, where now you add the output of the first stage and the second stage by using a capacitive coupling circuit to the bandpass filter amplifier. Now the output, the way in which you generate the spikes again is using asynchronous delta modulation. And the way that it's different is instead of you doing synchronous sampling, where you send off or you sample the analog amplitude of the signal, what you do instead is that you look to see when the signal has changed by a certain amount, which is also called a delta. So it's very similar to DVS, right? So you send the on events when the signal changes by a positive delta, and then you send the off events when the signal drops by a particular delta. So the output of this signal modulation is also communicated to the asynchronous logic. And so here's a very simple circuit diagram of how we create this asynchronous delta modulation. So here's the input coupling to amplifier. And now the output of the ADM, when it changes past a certain threshold, then you create an on spike. If you now drop below the lower threshold, then you create an off spike. And then there's the asynchronous logic that talks to the AER arbiter that deals with the request and acknowledge that you need. So these are the handshaking signals that you need to send the spikes off chip. And whenever any one of this request is made, then the asynchronous logic also comes back and subtracts the particular delta from the ADM output. Now, if you look now at the transfer function of first the output of the bandpass filters across the 64 channels, and so this is set for a Q of 1, you can see that the transfer functions are very well matched. And now if you also look at the spike outputs of the asynchronous logic, in this case in response to a chirp response, where you have you start off with a 6 hertz frequency going to a 21 kilohertz frequency over 75 seconds, then you can see the channels that respond change as you increase the frequency. Right? So it's quite nice, the response of this particular cochlea. You can now increase the Q of the filter to 10, and now you can see that the transfer function is a lot more peaky. And again, across the 64 channels, you can see that the transfer function is very well matched, right? And for the chirp response, because the Q is so high, then you can see very few channels respond this time to the frequency that's seen at that time. And so here's a video of what you get from the 64 channel output for speech. So you can see a stream of spikes going by as someone says some sentence. I don't remember what this was anymore. And then you can play a sentence from a particular sound database called Timid. This is one of the favorite sentences in the database. She had your dark suit in greasy wash water all year. And you can compute a spectrogram of the sentence for different frequency bands. And you can see, of course, certain patterns depending on the word that's spoken. And if you now take the spikes from the cochlea, play that same sentence to the cochlea, take the spikes, bin them in 5 millisecond bins or 5 millisecond frame. And what you see is, you see a very similar pattern, right? So you can see here for the different words, you can see very similar patterns that show up. And to know that the spikes carry the information about the original sound. So what we're going to do is to take the spikes and reconstruct the sound, And so here's the original sound.
She had your duck suit and greasy wash water all year.
And this is what we reconstructed from the spikes.
She had your duck suit and greasy wash water all year.
Okay, so now going on to audio edge. So now we're going to take the neuromorphic feature extractors, and then we're going to add a network behind it. Okay, so now we have, again, the two options. We can take the microphone input going to an ADC doing the FFT. And what you usually do here is that you feed it into a synchronous deep neural network. Now for the neuromorphic feature extractor, you have the output of the microphone going to a set of bandpass filters. You can either, some people create spikes directly from the bandpass filters. This is option 2, or sometimes you rectify the signal and then you send it to the spike generation block, right? And so the nice thing is that with this asynchronous output, you can create features that you can either use to drive a synchronous deep neural network, or you can also use it to drive an asynchronous spiking neural network. I'm going to show you more about this option that goes to a synchronous neural network. So for the 3 different tasks that we talked about, we're going to take the feature extractor features, and then we're going to drive a deep neural network, which can be either of these 3 types of architectures, right? Multi-layer perceptron, recurrent neural network, or convolutional neural network. But in the results that I'll show you, they're coming mostly from the recurrent neural network. And for the specifications of the edge audio device, what we care about is that the device has a low power consumption, a low memory footprint, and low latency. And so let's see how we can optimize the network so that we can satisfy these 3 criteria. So what we also did was we estimate the network power that we need for each of these edge audio tasks. And so what it shows you is for the voice activity detection, you don't need a very large network. And so the power that you use is very low. And if you now want to solve a speaker verification task, then the power that you need would be higher. And if you do speech enhancement, it's also higher. If you do keyword spotting, also higher. And if you really want to do speech recognition, well, it's about 100x increase from a voice activity detection network. And because of that, what you want to do is a hierarchical kind of task where you do VAD first. And if VAD says, yes, there is a voice, then you do any one of these other tasks, a speaker verification task or keyword spotting, speech recognition, and so on. So that lets you save power. Now let's look at the ways of achieving low memory footprint. And so these are the ones that are usually suggested nowadays for making a network small. So you have to reduce the needed resource by first reducing the bit precision of the network parameters, of course, also guaranteeing that the task accuracy hasn't dropped. And the reason for wanting to, the reason for wanting to keep the bit precision down is that you use less memory. And then the other thing is you want to prune away the weights or the neurons, or both, right? And what this means is that you need, then you get sparsity in storage or memory for the weights, neurons, and the activations. And so here's an example of the amount of energy per axis for a 64-bit word when you want to fetch something from memory versus the energy that you would use to do a multiply, either with a floating point or integer. And so if you want to fetch something from 8 kilobyte memory, you will burn 10 picojoules in a 45 nanometer CMOS process. So this was numbers that Verma collected in the 2019 paper. So you can see the memory axis is much higher than doing a multiply, even for a floating point 32. And if you want to use a much bigger memory, you can see that this energy per axis increases with the memory size. So it's good to have a much smaller memory size by doing any one of these operations here. So pruning just implies that if I've got a network like this, I train the network so that I can prune away either the neurons here or also the weights or the connections. Okay, for example, by dropping the neurons, you've dropped off a bunch of the weights. The other way of reducing compute is by skipping over zero activations. This was also called zero skipping, and it was also implemented in the convolutional neural network accelerator from our group, also called NowHop. And so what that means is when you have this operation where you multiply a vector by a weight matrix, then if you see zero activations, if you see zero inputs over here, you skip over it. You don't do the multiply because there's no need to do that. So basically, if you have now a 1/5 versus a 5/5 weight matrix, you can, in this case, narrow it down to a 2/5 vector and multiply by a 5/2 weight matrix. So you can save a lot of computes by skipping over zero activations. And the same thing with the weights. So here again, you have a whole lot of weights that are zeros. And so you can skip over all the zeros. Doesn't matter what the value is for the input vector. And so you can reduce it to a much smaller input vector and also weight matrix. And the other thing that I want to talk about is that you can also skip over computes in the temporal domain. And this is in part inspired by the spiking neuron model. And this is the work that we have called the Delta network. This Delta network came about because of what we see in the brain, and we call this event-driven computing, where now if you look at any one of the neurons in the brain, you can make a model where if you record from intracellular from within the neuron, then you can make a very simple model of this neuron. So basically it's spikes coming in, summed together after you've weighed the input spikes. And then if the sum of this weighted input crosses a threshold, then you put out another spike. So the normal way of running a synchronous CNN is in the frame-driven way, where you update one layer of neurons at a time. Sorry, but I have to. Okay, so in this event-driven way, what we want to do is we don't want to update all the neurons. Instead, we want to look what we call active neurons. Right? So for example, the ones here in orange are active. And then all we need is to fetch the weights of those active neurons and then update all the neurons in the next layer, then figure out which ones are really active. And then we update the neurons in the subsequent layer. And so this is what we call the Delta network algorithm. And just an animation to show how it works. So here we have the neurons where their activation level is this much at a particular time step. We put a threshold on top of this level. And then the second time step, we look to see if the activation has increased past this threshold. So in this neuron, you exceeded the threshold, in this neuron not. So it's inspired also by the spiking neuron model where there is a threshold. So because this neuron exceeded the threshold, then this is called the activated neuron, and this one is not activated. So now we do this for a whole layer of neurons. So this is where they start off with. You put the threshold on all of them. Look on the second time step whether you exceeded the threshold. So you can see this one did, this and this one. And all you need is to fetch the weights for these three neurons and then use it to update the next layer. So Cheng Dao, a student of ours, have implemented this network on different FPGAs. So this is the one called HDRNN, implemented on the Mini Z. What he implemented was a 2-layer 768 hidden unit, gated recurrent unit, RNN, recurrent neural network. This is a network that was trained on a TI-digit speech data set. This is the numbers he got by doing a batch 1 inference. And so you can see that as you increase the threshold, that the neuron needs to get activated, your effective throughput measured in gigaopt per second increases, as you would expect, right? Because you're doing fewer and fewer fetches of the connections from the activated neurons. At the same time, you also have to look at the trade-off on the word error rate of the TI digits test set, right? And also, as you expect, as you increase the threshold, at some point, the word error rate should go up. But you can see that you can actually increase it by quite a bit before the word error rate increases. So this is what we're looking for in order to reduce the number of computes in the network. So we've done a demo where we connected this delta network with features extracted from the spikes, right? So we call this feature extracted features. And then we trained the delta network to recognize labels from a simple continuous speech recognition data set. So in this case, actually just recognizing digits. And the way that we extracted features from the spikes is by doing a spike count feature. So basically we set a particular frame time, and then for 3 different channels, we count out the number of spikes. And so you can see in this case, you get 2, 3, 1. And then in the next frame, you'll get 1, 1, 3, because there are 3 spikes here and 1 in the other 2 channels. And the same thing for this one, you get 3, 3, 3. And then you get 2, 1, 0. So now you feed these features into the delta network. You can train it as a delta network, or you can train it as a normal network, and then impose the threshold. Here's a demo of it working. So you're going to see on the screen here the spikes coming from the channels, and then what you see here are the labels of what the network recognized from the sound coming in. And so here you can see the dashboard connected to an FPGA, which runs the delta network. And so you'll see Cheng.
2, 3, 4, 5, 6, 7, 8, 9, 0, 0, 0.
So I hope you guys all saw that. Okay, so what would be nice is if you take now this cochlea chip and this FPGA that's running the network, and then you combine them together into one ASIC. Yeah, because then you'll get the best of a lot of things. And so this is what we just reported at ISSCC just a couple of days ago. It's a keyword spotting ASIC. It's done by Kwante Kim and Cheng Ao. And so Kwante designed the analog front end, and Cheng designed the digital backend all on one ASIC. And so we've got an asynchronous domain, which is the analog front end side, and then a synchronous domain because of the digital backend. And what we did was we tested this on the Google speech command data set. It's a data set that's used by many of the groups building tiny ML, tiny machine learning chips in the ISSCC community. And so here for a particular word, yes, you see from the different channels, you can see the features corresponding to the word E and then S, right? So the S has high frequency. So you can see these channels with highest center frequency produce features and not the lower channels. And for this Google speech command data set, there are 12, well, actually there are 10 keywords plus 2 unknown words. And so in this case here, you see the confusion matrix for the ground truth versus the predicted word from the network. And also here we plotted the positive rate of the different keywords, right? So certain keywords are much easier to recognize, like yes and stop, right? And let's see now what's not so good, like off is not so easy. This might take, so actually, Arindam, am I running out of time? So
yes, Shih-Chii, I think you are about 5 minutes left.
5 minutes left. Okay, all right. So this is great. So you guys can see the slides or go go to the ISSCC recordings and you'll see this also. So what we want to do here is to compare 5 different designs, including ours. Actually, this is also, Minhao's work. And anyway, this designs all use analog feature extractors, built in different processes. Okay, so you can see the architectures are slightly different. So this is GMC bandpass filters, and then this is for this particular one that I just talked about. It uses an oscillator-based bandpass filter. And we had a figure of merits. I think that's quite important when you compare against these different designs, especially in the ISSC community, right? Because you have to say how good is your analog feature extractor. So in this case, it's defined as the dynamic range, the input dynamic range of your design plus log of 1 over the P norm. So P norm here is the normalized power that you get for 200 kilohertz channels, and the frame shift. So the frame shift is just the amount of time that you need to get the features from your input. And so just to show you, for example, this design over here, their frame shift is 512 milliseconds, even though their power is only 0.06 microwatts. And that's because they're running the clock very slow. This is the power that we consume on this chip. But if you do the FOM, we have a FOM number that's slightly higher. Okay. And also, this is the first one that has an analog feature extractor, but does keyword spotting instead of a voice activity detection. Okay, and I won't go over the rest of it. There are also a few designs reported at ISSCC or VLSI or CICC, and these are designs that also use the conventional feature extractor, digital feature extractor, also tested on the Google speech command data set. So for example, this design's over here. And so ours compared to the best one also recognizes 12 keywords. Yeah, so we have almost similar accuracy. Okay. So we're happy because this uses an analog front end. Okay, so to summarize the tutorial, so gave you a survey of silicon cochlea designs in your operation, showed you a way in which computation could be executed on demand, similar to a spiking network. So networks process only when your inputs have changed. And we hope this will lead to new solutions for low power hearables and IoT smart sensors. And so we believe that the low power and low latency edge audio that's really needed can be achieved by sparsifying the number of computes and also processing on demand. Okay, and if there are any questions? Yes,
thank you so much.
Thank you
for the wonderful talk. Thank you. Thanks a lot. So we do have a couple of questions on the chat. I don't know if you can see it. Otherwise, I can read them out for you. Can you see the questions?
What advantages will using a silicon cochlea confer over signal processing neural network way for feature extraction and beyond? What is our motivation for exploring this? Yeah, so it's a very good question. So we are considering edge audio because in edge audio, you don't need very big networks and you don't need to do a very complex task. So if you want to do something like, speech recognition in the way that you would like, for example, when you ask Alexa a question and Alexa gives you the answer, for example, where the best restaurants are, then you should use the conventional way. You have to go up, you have to send your speech up to the cloud and, pass it through an NLP network, right? A natural language processing network. That's the way to do it. But for simpler tasks like voice activity detection, you don't need such fancy networks. And so that's where we believe these applications are just perfect for the neuromorphic sensors, in this case, the cochlea. And the next one, is there any commercial available silicon cochlea? No, there isn't. I think it's, there's a lot of cochlea designs that have been done, and what needs to be done also is to be sure that the output of these cochleas are useful for solving the kind of problems that people might be interested in. And this has taken quite a bit of time. And actually the design that was done by Minhao is actually quite a nice design. It's just that we don't have the resource to make the how do you say it, the product so that somebody else can buy. Because you need to raise quite a bit of money then. And then you need to, and if it's just the researchers who would like to use it, then it could be quite expensive, right? Because to get things down in price, well, you need to sell lots and lots of it. So that's why. What are the ASIC challenges, if any, your group had to face in desk designs? Yeah, actually quite a bit. I think a lot of it is dealing with analog mismatch, right? Because even though sometimes we suggest that with analog designs, you get a feature because mismatch could be a feature. But when you want to use the output of these filter channels, you have to have, either you have an algorithm in place that can deal with this mismatch, but if your algorithm does not deal with mismatch, then you need to make sure that you have very good matching across the filter channels. And because of that, then you have to do very good analog design, right? Ensure that the mismatch could be low for your circuits. And also low power is also very important, along with circuits that operate under low voltage supply and also dealing with technology scaling. No more questions. What?
There is one more.
Oh, what are the applications where real-time edge audio processing has the highest market? Boy, this person's so keyword spotting. Definitely. Voice activity detection and keyword spotting will be a good place. And there are many devices that use voice command nowadays. So if you have like a little module that can do this edge audio task up front before you actually now send the speech out to the cloud, if you have to. And this would be I think it would be a great application. Okay, no more Q again.
Okay, so maybe I do have one question for you. So do you feel that this kind of technology has a good application in hearing prosthesis?
In hearing prostheses, you mean in cochlear implants, or you're talking about
either cochlear implants or
hearing molds?
Yeah,
hearing aids.
Hearing aids or cochlear implants. Has there been any work in this direction?
Yeah, there's been quite a lot of work in this direction from the research, from the academic community. What's difficult is that the companies hate to change their product, right? Because it costs them more than $10-20 million to change, for example, the machines that make the mold to hold the electronics for the hearing aids, right? And so they have to understand whether the solution that you're proposing will give them back this 20 million plus the profit, the additional profit they're going to get from this, from your new solution. Right?
I guess any changes would also mean a lot of approvals to get for anything that's related to biomedical.
Yes, exactly. Yeah. So you need more, you will need a new approval.
Yeah.
Certificates and so on.
Okay.
So I think, I'm not sure. I mean, I think it gives you ideas of where you could apply some of the circuits, but probably want to think more than that. Think bigger than just hearing aids.
Okay.
I personally think, For example, you combine it with DVS, right, to do something maybe more informative, right, by having two different sensors that give you more information, probably in complementary ways.
Right.
Yeah.
Okay, great. I mean, thanks a lot, Shih-Chii, for taking time out. I know it's really early over there. So thank you once again. And I think let us thank the speaker.